how does one go about using quantum states themselves to share another quantum state? And this would probably ring bells and remind us of quantum teleportation, where there are two users who are non-locally present in two different distant end nodes. And one of the end nodes wants to share or distribute this particular state that she has to the other end node without actually transmitting it, but they want to use an entangled pair that they have between those two end nodes in order to have this quantum state teleported to the other end node. And how is this done? In teleportation protocol, the first end node who has the quantum state performs Bell state measurement with her photon in the entangled pair that is distributed across these two end nodes. And the result of the Bell state measurement is shared with the other end node, and the other end node user now applies correction operations on his photon, and that would result in the photon that he has transformed into the same state that Alice originally had, or the first node originally had. So you'll see a lot of equivalence between the protocol that we're discussing today. The key difference here with quantum secret sharing is the dealer, or in this case, we'd be defining the dealer as Alice, is sharing the key or sharing the secret across two users, and neither of them should be able to reconstruct the state that she wants to share with them. Only if they both collaborate, they should be able to reconstruct the state. So that having defined the goal, let's dive into how this actually works. Here, the three, in this case, we are considering three node network. Alice, Bob, and Charlie are the three nodes in the network, and Alice is the dealer who has the secret quantum state. To begin with, Alice, Bob, and Charlie have a multipartite entangled state, specifically tripartite entangled state, GHZ state, which is of the form 000 plus 111, as shown here, that is distributed across all these three nodes. So they have one photon from the state each. Subsequently, Alice uses her photon from the GHZ state to perform Bell state measurement with her secret quantum state, which we call here as psi A, has probability amplitudes generically alpha 0 plus beta 1. And based on her Bell state measurement result, which could be one of the four Bell states, we are considering that for simplicity here. Oftentimes in an optical network with linear optical elements, for Bell state measurement, it would be 2 out of the 4 rather than all the 4 possibilities. Let's take this generic case of all 4 possibilities, our outcomes that she can measure from her Bell state measurement. She's going to communicate that to Bob and Charlie, and Bob and Charlie will first have to perform polycorrection operations based on the Bell state that Alice measured, but subsequently they also have to perform a control gate that will allow for either one of their photons to become the same quantum state or take the same quantum state that Alice wanted to share with them. And we'll call that psi B or psi C here, but essentially it's the same alpha 0, beta 1 that's reconstructed. And how does this happen? Essentially because of the entanglement in the GHZ state, the Bell state measurement collapses Bob and Charlie's joint state to have the probability amplitudes that Alice's secret state had, and that is finally, after the controlled operation, resulting in the same exact state that Alice wanted to share. So this outlines this teleportation-like protocol that is used for quantum secret sharing.